Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We have been looking at various subsystems, and lately we have been looking at the input output subsystem. With respect to the input output subsystem, we have looked at some basics of how data is transferred on a bus. We looked at synchronous data transfer and asynchronous data transfer, and we also looked at how input output commands are given, how there are registers, input output registers which are used in the device controllers, and how these are controlled by the processor. So, we also talked about different addressing schemes there, the IO mapped addressing scheme and a memory mapped addressing scheme. So, what we will be looking at in today's topic is how the data transfer actually takes place. So, when we talk about data transfer, there is a basic challenge that we need to address. The basic challenge is that the rate of transfer to and from the IO devices is normally slower than the speed of the processor. That is, the rate at which data can be transferred is slower than the speed of the processor. So, therefore, there is a need for us to synchronize the data transfer between the processor and the IO devices. One of the simple mechanisms that has been used for doing this is a program controlled IO, or what is referred to as the polling mode of operation. Now, we have looked at this in the previous class. So, in the polling mode of operation, what we do is that the processor repeatedly monitors a status flag to see whether a device is ready for the data transfer, and then when it is ready, it takes the data from that. So, this is called as the polling mode, and we have seen that this is a very slow mode of operation. So, in order to make things faster, there are two other mechanisms that we look at. One is called the interrupt mode of data transfer, and the other is a direct memory access. Now, this is what we need to take a look at in more detail now. So, as I said, when we talk about interrupts, these come basically because we want to save the processor's time. Because in the program controlled mode, what normally happens is that the processor is wasting a lot of time. That is, when it is continuously monitoring the status of the device, it is not actually performing any useful task, because it is checking it. If the device is not ready, it is again going to go back, do some other work, and then again come back and check. This time that it uses for checking again and again is basically a waste of time. Okay. So, the alternate approach that we are talking about is the interrupt driven mechanism. In the interrupt driven mechanism, what we are saying is that the IO device will alert the processor when it becomes ready. So, we do not want the processor to keep checking again and again, but it is the responsibility of the IO device to alert the processor when it becomes ready. Now, how will it alert the processor? We use a special hardware signal which is called the interrupt. Okay. So, the device will alert the processor by sending a hardware signal called an interrupt to the processor. When you say it is a separate hardware signal that is to be used, normally one of the bus controls lines that we have, okay, is dedicated for this purpose, and it is normally called as the interrupt request line. Okay. So, we have an interrupt request line which is used as a dedicated line to indicate to the processor that an interrupt is being generated by a particular device. Okay. So, this is how we normally handle the interrupt. So, we have a special signal called the interrupt signal which is given to the processor, and a special interrupt request line which is normally dedicated for this purpose, which is there as one of the control lines in the bus. Now, what does the processor do when it receives an interrupt? What it will do is that it will respond by stopping its current activity and service the interrupt. When you say service the interrupt, it basically will look at what is causing the interrupt. If it is an input device causing the interrupt, then it will do the input activity. If it is an output device causing the interrupt, it will do the output transfer. Okay. So, to do this, the processor will execute what is called as an interrupt service routine. So, the term that we normally use is interrupt service routine, or ISR, indicating that the interrupt is being serviced. So, let us look at how this interrupt service routine typically is handled. Okay. So, now let us look at what we have. You have your processor executing some set of instructions. So, let us say we have instructions going from 1 to m, okay, and when a particular instruction I is being executed, an interrupt occurs. Okay. So, that is the instruction which is located at address I is being executed. At this time, an interrupt has occurred. So, what are we saying? We said that the processor will stop whatever it is currently doing, right, and then it will service the interrupt service routine. So, let us see what will happen then. So now what happens is, when you have this interrupt occurring over here, there is another interrupt service routine. So you can see that this is located at some other address. So this interrupt service routine, which is located at some other address, is now called by the processor. Okay. So this interrupt service routine will be called between the instruction I and I plus 1. So that is, it will stop the, once the interrupt occurs, it will finish the execution of this instruction I, okay, or depending on the type of interrupt that you have, and it will go and execute this interrupt service routine and then come back and then continue at the instruction I plus 1. Okay, this is what will be done. Okay. So now when you transfer control to this interrupt service routine, now how do you normally transfer control? It is done normally by changing the contents of the program counter. Remember, our program counter is the one which keeps track of which is the instruction that is currently being executed. So when I want to now branch off to another routine, the interrupt service routine, okay, what we have to do is we need to change the contents of the program counter. Okay. But what we need to also do is, before transferring control, okay, that is by before you change the contents of the PC, we also have to store the value, the current value that was over here, right, or the current contents of the PC, that is, which is I plus 1. Now remember, when an instruction I is being executed, the program counter will already be pointing to the next instruction that has to be executed, right. It would have been incremented to point to the next instruction, so that will be fetched next. So now what we therefore need to do is save the contents, this I plus 1, which is the contents of the PC, that will have to be saved in some special location or in some known location. Now why do we need to save this? So that when you finish the interrupt service routine, you are able to come back to this position and resume the activity from here. Okay. So remember, the interrupt service routine is something which is disrupting some activity that is happening. So since it is disrupting some activity that is happening, we need to save wherever we have been disrupted, right. So that location has to be saved so that you can come back and continue from where you left off. Okay. So this is an important activity that we always need to do whenever an interrupt service routine is handled. An interrupt occurs at address I plus 1 has to be stored, and this return address, this I plus 1 address is normally referred to as the return address, and this return address is usually stored on some special location. That special location, or in a known location, as we said, that known location normally happens to be the processor stack. So we just store it in the stack so that you can get it back from the stack. Okay, this is what is normally done for an interrupt service routine. Now you can see that handling of this interrupt service routine is very similar to handling of a subroutine. Okay. Now what is a subroutine? It's a function, whatever that is being called when you have a particular program being executed, right. You can see that the treatment of an interrupt service routine is very similar to that of a subroutine, but there are some significant differences. So let us look at what those differences are. You can see that a subroutine performs a task that is required by the calling program. Okay, that is what normally happens. A subroutine is something which is almost something which the calling program knows that it wants it to be done. Okay, whereas an interrupt service routine may not have anything in common with the program that it interrupts. Okay, so we see that this program is different from this interrupt service routine. If this was a sub-program, this is something which should have actually been called by the program itself, right. So that is one significant difference that we need to note between a subroutine and an interrupt service routine. So a subroutine performs a task that is required by the calling program, whereas interrupt service routine may not have anything in common with the program that it interrupts. And it is also possible that the interrupt service routine and the program that it interrupts may belong to different users. When you have a multi-user scenario, your program that is being executed may belong to another user, and an interrupt service routine that now needs to be called, or an interrupt that occurs, may belong to another user. Okay, so this is another difference that you could have. Okay, so as a result, what is it that we need to keep track of? What we need to do therefore is, but before branching to the interrupt service routine, normally not only the PC, but other information such as condition code flags and processor registers used by both the interrupted program and the interrupt service routine must be stored. Okay. So we talked about saving the PC contents. So what we are now saying is that not only the PC contents that need to be saved, but also other information, other status information such as the condition code flags and other processor registers will have to be saved. Okay. So this will enable the interrupted program to resume execution upon return from the interrupt service routine. Okay. This is another important aspect to be remembered. Okay. So now when we talk of this saving and restoring information, so you can see what is happening. So when the interrupt service routine is taken, that is when the interrupt occurs and you are jumping to the interrupt service routine, you will be saving the contents, and when the interrupt service routine completes and you come back, you will be restoring the information and then you will start the execution of the original program. So, you can see that this saving and restoring involves memory transfers, because we said that we normally save it by storing it in the stack. So, now stack memory is a memory location. Therefore, when you say saving and restoring registers, it involves memory transfers. Now, remember that memory transfers always take up time. So, this process of saving and restoring registers increases the total execution time, because you need to be saving into memory and restoring it back from memory. Okay. So, what also therefore happens is that it increases the delay that you have between the time that an interrupt request is received and the start of execution of the interrupt service routine. Okay. So, remember, the interrupt service routine is the one which needs which actually has to do the action required for that interrupt. Okay. But you can see that before you actually start the action for that interrupt, you are doing some extra work, which is saving the current context of the program that is under execution. Okay. So, this delay that you have between the time that your interrupt occurs and the time that the actual interrupt service routine starts, that is called as the interrupt latency. Okay. Now, this is important because when we have certain critical interrupts which need to be handled very quickly, then we need to make sure that the interrupt latency is kept to a minimum. Okay. So, that is an important aspect that we need to remember. Okay. So, now to reduce the interrupt latency, what is it that we need to do? So, obviously, what is it we should do? If we save minimal amount of information, that automatically will reduce the interrupt latency. So, what most processors therefore do is they only save the minimal amount of information. Now, what is the minimal amount of information? Typically, it includes the PC, the program counter, and the processor status registers. Okay. If any additional information must be saved, it must be saved explicitly by the program instructions at the beginning of the interrupt service routine. Okay. So, normally you save only minimal information, and if any additional information that needs to be saved, you do so explicitly. This is how we try to keep the interrupt latency within a manageable number, or which is within a small amount. Okay. Now that you have serviced an interrupt, okay, by means of an interrupt service routine, we also need to let the device which has caused the interrupt know that it has been serviced, right, or that its interrupt has been accepted by the processor. So, what do we do for that? So, for this we use a term called interrupt acknowledgement, right, that is the processor acknowledges to the device that the interrupt has been serviced. Okay. So, how do we generate these interrupt acknowledgements, and how do you indicate to the device that the interrupt is being acknowledged? Okay. This can actually be done in two ways. Some processors, what they do is they have an explicit signal called the interrupt acknowledge signal, which is used for this purpose. So, just as we talked about an interrupt request signal, which is an explicit control signal, right, we can also have something called an explicit interrupt acknowledge signal, which is given. So, what will happen is that when the interrupt is processed, this signal, the interrupt acknowledge signal, will be activated by the processor, and that will be an information to the device that its interrupt is being serviced. In other cases, what we can also do is the data transfer that actually takes place between the device and the processor can be used to inform the device. In response to the interrupt service when the interrupt service routine is called, okay, there will be some data transfer that will take place. So, as part of the data transfer, an acknowledgement information or an acknowledgement note can be given to the device. So, this is another method that can be used. Both these methods are widely in use. You can have interrupt acknowledgements used in some processors, and in some processors it is done by means of an interrupt as an acknowledgement message that is given to the device. We will take a short break and then come back and continue with other details of the interrupt servicing mechanism. Welcome back after the break. So, we have just been looking at different details of the interrupt servicing mechanism. So, now there is another important aspect that we need to look at. Now, is it possible for me to suppress the handling of some interrupt? Now, we said that any device, if an IO device, when it wants the services of the processor, will do so by generating an interrupt. Now, is it possible for the processor to suppress the generation of an interrupt by a device? Now, obviously, we may need a mechanism for this, because there are certain activities that may be taking place which should not be interrupted at all. Okay. So, in that case, we need to have a mechanism by which you are able to suppress an interrupt. So, this is normally done by what we call as enabling and disabling interrupts. So, we have this process called disabling interrupts, which is normally used. There are different situations in which we may need to disable interrupts. One such situation is basically this, which is that, for instance, the processor may not want to be interrupted by the same device while executing its interrupt service routine. So, this is a very peculiar scenario or a typical scenario as such. Now, look at this. You have a processor which is interrupted, and when the processor is interrupted, it moves to the interrupt service routine and it is servicing that interrupt. Now, while it is servicing that interrupt by means of by executing that interrupt service routine, it may not want to be interrupted again by the same device, okay, in which case you may want to suppress the interrupt. So, this can be done by means of this mechanism called disabling of interrupts. Okay. So, how do you do this disabling of interrupts? Normally, there are some simple machine instructions provided called interrupt enable and interrupt disable. Using these instructions, you can enable and disable the interrupts. Now, this may be done by means of separate instructions, or it may be handled with the help of certain bits which are provided on the device, which is called as an interrupt enable bit. So, if you are able to set or reset this bit, that will amount to enabling interrupts and disabling interrupts. Okay. So, this is something which is done. So, typically what we do is, when you have an interrupt service routine being executed, if you want to avoid interruption by the same device during the execution of an interrupt service routine, so what you would normally do is that the first instruction of an interrupt service routine can be an interrupt disable instruction. What will be the effect of this? That interrupts from that particular device would have been disabled, and the last instruction of the interrupt service routine can be an interrupt enable instruction. So, the effect of this will be that between this first instruction and the last instruction, no interrupts from this particular device will be entertained, and you definitely need to have an enable as the last instruction, because if you did not enable it, it will be permanently disabled, or it will be disabled until you enable it again. Now, so which is why normally when you disable an interrupt, you always have to keep track of when you have disabled the interrupt, and make sure that you enable the interrupt. Otherwise, interrupts from that particular device will not be handled correctly. Okay. So, we have to be very careful about using this enable and disabling of interrupts. Okay. So, this is one important aspect that we need to understand. Another aspect that we need to understand is what happens when there are many interrupts that are being generated. So, now whatever we looked at was, we said, okay, when one interrupt occurs, what is it that needs to be done is what we looked at. So, what we are now talking about is, now obviously there are many IO devices that are there. It is not only one single IO device which is there, but there are many IO devices. So, when there are many IO devices, it is possible that many of them would be generating interrupts, right, simultaneously. They could generate interrupts simultaneously. There is no order in which interrupts could be generated by different devices. So, when such situation occurs, how do we handle it? So, the question basically is, how do I handle multiple interrupts? So, we need to have mechanisms to determine how multiple interrupts are handled. Now, the reason that we need to worry about this is that each device operates independently, and so we cannot impose any order, right, and hence no definite order can be imposed on how the devices generate interrupt requests. So, what are the issues that we need to consider when we handle multiple interrupts? So, that is what we need to understand next. So, the first thing that we need to look at is, how does the processor know which device has generated an interrupt? Okay, this is the first thing that we need to understand. Second thing is, how does the processor know which interrupt service routine needs to be executed? Remember that for different interrupts, different interrupt service routines will have to be executed. So, the processor will have to have a mechanism by which it is able to know which interrupt service routine needs to be executed. Third point that we need to handle is, when the processor is executing an interrupt service routine for one device, can another device interrupt the processor, right? So, we earlier we talked about whether we can allow the same device to interrupt the processor or not. Now, we are talking about whether another device can interrupt the processor or not when an interrupt service routine is being executed. Another question is, if two interrupt requests are received simultaneously, then how to break the tie? Okay, that is, we are talking about simultaneously receiving two or more interrupt requests. Then how do we break? That's a tie. How do you break the tie? Okay, all these are different issues that we need to worry about when we are handling multiple interrupts in a system. Okay, so let's look at the first thing, which is identifying the interrupt. Okay, so when the processor receives an interrupt request over a control line, how does it know which device is requesting an interrupt? Okay, this is the first question that we need to look at. Okay, normally this information would be available in the status register of the device which is requesting an interrupt. Now, we talked about every device will normally have a status register and a command register. So, in the status register, one of the bits there will be what is called as a request bit or the IRQ bit or the interrupt request bit. Okay. Normally, this is set to 1 when that particular device is requesting an interrupt. So, all we need to do therefore is the interrupt service routine can poll this IO devices which are connected to the bus, okay, and the first device which has the IRQ bit set equal to 1 is the one that needs to be serviced. You can identify that as the device that needs to be serviced. Polling mechanism is easy, but again as we said, polling is always time consuming because you need to go and query the status bits of all the IO devices which are connected to the bus. Okay, that is a difference that we need to keep in mind. Okay, so polling may not be a very efficient option. So, we can go for other mechanisms. Again, you can let the device itself know that it is the one that is caused the interrupt. So, how do we do that? Okay, how do we allow the device to identify itself directly to the processor? So, that can be done by means of what is called as a vector or a special code that is sent by the device. Okay, so device can do so, can identify itself by sending a special code, normally this can be 4 to 8 bits, called the vector, to the processor over the bus. Okay. Now, this code which is supplied by the device may represent a part of the starting address of the interrupt service routine. So, it can also be used to identify which is the interrupt service routine that needs to be handled. Okay. So, now how do you when do you actually specify this vector? Okay. This is normally done in response to the interrupt. That is, when an interrupt request we said is generated, the processor can respond by giving an interrupt acknowledgement signal. Okay. An interrupt request signal is given to the processor responds by giving an interrupt acknowledgement signal. So, when this acknowledgement signal is given, at that time this vector or the special code can be sent over the bus by the device to the processor. So, when this vector is received by the processor, then it uses that information which is available in this vector to identify which is the device which is interrupting the processor, and then it branches to the corresponding interrupt service routine. Okay. So, this is normally a process that is used which is called as the vectored mode of operation. So, when you have a vectored mode of operation, the device identifies itself as the interrupting device by sending this vector to the processor. Okay. This is a very commonly used vectored mode of operation that is used for identifying interrupts. Now, when you specify the vector, as I said, the vector can be used for identifying the starting address of the interrupt service routine also. So, how is that done? A part of it will come from the vector, and the remaining part of the starting address is obtained by the processor based on other information such as the range of the memory addresses where interrupt service routines are located. Now, normally what happens is that all these interrupt service routines, they are special routines. So, they are normally located at some specific memory locations. Okay. So, for instance, if you have an interrupt vector 1 being specified, 1 multiplied by some number may point to a particular interrupt service routine. So, you can look at the vector as some kind of an index to the interrupt service routine, and you can derive the interrupt service routine address from this vector and jump to that particular location and start executing it from there. Okay. This is what we normally do in order to identify the location where the interrupt service routine would be present. Okay. Next thing we talked about is interrupting an interrupt, right? That is, when an interrupt is currently being processed, can another device interrupt it? So, how do we do that? If I do not want other devices to interrupt it, I will have to disable the interrupts. Okay. So, one option that we have is to disable the interrupts from other devices. Okay. So, during the execution of an interrupt service routine of a device, the processor may not want to accept interrupt requests from any other device. So, what it will do therefore is it will do what is called as an interrupt disable bit will be set. Okay. There is an interrupt enable and a disable bit, and that bit will be set. So, if that is set, then any interrupt, no interrupt will be handled by the processor. Now, normally the question that we can ask is it a right thing to do? What if there is an interrupt that needs to be processed at that time? So, the answer to that normally is that these interrupt service routines are normally kept very short. So, because they are short, when the interrupt service routine is being executed, even though we do not accept other interrupts, the delay that you have before you process the next interrupt is normally small, because we said that the interrupt service routines themselves are short. So, because they are short, you can come back after a little while and then come and service the interrupt. Basically, what we are saying is we are not saying that we won't handle interrupts at all. All we are saying is that the handling of the other interrupt will be delayed when this particular interrupt service routine is being executed. But what can also happen is that for certain devices this delay itself may be unacceptable. You may not be willing to wait for this small delay. Okay. So, in which case can I say that some device will be allowed to interrupt the processor even when it is executing an interrupt service routine of another device. Okay. So, that is we are looking at a special case where we say delays are unacceptable minus this particular interrupt has to be serviced immediately. So, how do we do that? Okay. This is normally done by by using something called priorities. Okay. That is, we say that certain devices have a higher priority. So, if a device has a higher priority, then its interrupt will have to be handled immediately. Okay. So, you can say that you can have a series of priorities. Okay. You can have priorities ranging from 0 to 7 for instance, and say that 0 is the highest priority, 7 is the lowest priority for instance. So, if I have a priority 0 interrupt coming in, it will have to be immediately serviced irrespective of whichever other interrupt service routines are being executed. But if I have a priority 0 interrupt being serviced and I have an interrupt with priority 7 coming in, that will not be serviced, that will be suppressed. Okay. So, you can use this idea of priorities to determine which devices need to be which devices interrupts will have to be serviced immediately. So, we have this thing called a priority structure which is used. So, an interrupt request from a high priority device is accepted while the processor is executing the interrupt service routine of a low priority device. So, therefore, what we need to do for this is that we need to assign priority levels. Okay. So, a priority level is assigned to a processor, okay, and it can be changed under program control. So, how do I assign this priority level? This is normally done by setting something called a priority bit or whatever which is there in the process status register. So, you will have the priority of the current program that is being executed available in the process status register. So, if you have an interrupt coming in which is higher than that particular priority, then it will be accepted, otherwise it will not be accepted. Okay. So, this is how we handle devices with different demands or different priorities. Okay. Devices with different demands are handled by giving them different priorities. Okay. This is how things are handled. Let us summarize the contents of today's lecture. So, you looked at various aspects of interrupts. We looked at the interrupt service routine, and then we talked about handling multiple interrupts. When we have multiple interrupts, we looked at identifying the device which has caused the interrupts, identifying which is the interrupt service routine to be executed, how simultaneous interrupts are handled, and we talked about priorities. We also talked about enabling and disabling interrupts. So, questions to review the contents of today. Question number 1, why is the interrupt mechanism better than polling? Question number 2, what are the steps taken by a processor when an interrupt occurs? Question number 3, what is the use of interrupt enable and disable bits? Question number 4, how does the processor identify the device that is causing the interrupt? Question number 5, what is meant by a vector in the context of an interrupt? Question number 6, why do we assign priorities to interrupts? Thank you.